Hey everybody! All right, this little video was kind of brought to me by a student. Um, Almost any math textbook that you have is going to include some kind of problem like this. So, so this is kind of a general sense. In fact, you can actually change these numbers here, 17 and 20, and make them A and B, and it doesn't change the problem significantly. All it does is it changes it from, hey, I know these values, to I don't know these values. So there are certain things you can do with it. Anyway, the idea here is that it is almost a question of Christmas. And the old, I don't know if they still make them. I assume they do, but the clothing boxes where they used to fold in on themselves, you get like 27,000 to a package about that thick, and then you'd have to unpack them and you'd have to open them up. It's very, very similar to that. And then the question, of course, becoming is how big should we make the tabs? How much of an area is this going to handle? How much volume? How many shirts can you pack into it? That sort of thing. So what we're going to do then is we're actually going to figure out some things about this and then kind of express them. So this thing, the structure of how to build it, that sort of thing after folding and cutting, it's called a net. And what's going to happen is we're actually going to cut out these little squares here. When that happens, we can then bring the sides in. Let's see if I can make this without screwing it up here. We can, in a sense, fold along the dotted line and create a box. And the question is twofold. If I have to paint this, meaning I have to give it some kind of a coloring, how much paint would I need, which is an area problem? And then if I were to fold that, how much could it hold, which is a volume problem. Now, in this instance, we're going to examine it from an algebra standpoint, and so we can't really do really super fun things with it, like figure out what's the best shape to make it to maximize volume. That's a calculus problem. Same exact setup, though. And so what we're going to do is we're going to express various actions of this on the basis of, well, how much do we cut out from each corner? And the assumption to make everything nice and neat and to make sure you have a nice not cubicle, but rectangular solid box. In order to do that, you want all of these cutouts to be exactly the same. So that's why that's why all of these values are x. You're going to cut out a square from each corner, some value of x. You don't know that value because it depends on the size of box that you want. So let's say we have this here, and what we want to know from this is, well, what is the area that we're going to cut out? So let's say total area of cutouts. Again, because when you produce these boxes, anything that you cut out is waste, which means you just threw away that money. Whatever the sheet costs, and minus whatever these things cost, okay, you just tossed out whatever the money that is. So you kind of want to minimize how much you cut out of things, because otherwise it's just wasteful. So we want to find the total area of the cutouts. Well, we notice that all of the variables are the same. Since all x's are the same, then they're at the same value. Whoops. Let's learn how to spell, shall we? Value is spelled with a U and then an E. And then, so what we can notice is then we're symmetric, meaning that all of these are the same. So we can figure out the value of 1 and then just multiply it by 4 because we have 4 of them. So the area of the cutouts is going to be of one cutout in this sense. One cutout area is equal to x times x, which is x squared. We have 4 of those. So 4 cutouts. My apologies. It's been a while since I made one of these videos, since I'm not used to that double screen thing I probably get rid of. But 4 cutouts area would simply be 4 times x squared, or just 4x squared. Okay, so now that's one question that we have, because we want to calculate how much waste we're going to have, because that's going to tell us how much money we're just throwing down the drain. So now we come to a different question, which is, okay, so once we cut out that area, how much area is left to either paint, or if it's a cardboard box, like a Christmas box, maybe we want to line it with a special paper, which means that we have to find out how much paper we need. So we want to find the area of what's left. So we could find the total area of these cutouts, and let's say, let's call this C of x. This was just simply the cutouts in reference to the variable x, and so we have 4x squared. So that's how we can express as a function, because we can stick this function into our computer, and then our computer will spit out all kinds of fun stuff. But we developed this function to describe the total area of the cutouts that we made in the box. The area of what's left, well, we're not dealing with a generic, we're actually designing this around this 20 by 17. So if we used the whole thing, the area of the whole thing, well, that's just equal to the length times the width, because we're assuming a rectangle. So 20 times 17, which is going to give us 340 square inches, and I probably don't want to do it like that because that's just confusing. Square inches. Or you can put IN and then the little square up top for inches squared, but that's fine. Either way. All right, so that's how much the area of the whole mess is. So then the question is, well, how much area is left? Well, what's left is the area of the whole minus what you've taken out. So we have our function, and it's the area of the whole minus what we've taken out, which is the cutouts. And so that would be an area function for the thing that is left. And then finally, suppose, and I'll try to draw this out here, suppose we fold it on the dotted line. Fold on dotted lines, and we make a box. So this box is going to kind of look like this. Pardon my drawing. I can make straight lines, but I can't guarantee that this is going to be in a good perspective. So we folded up the box, which is going to give us something that looks like this. Whoops. Wow, that was terrible. Let's try that one more time. Just go like this. Close enough. All right, and so then this guy comes down here, roughly in the same length, and chop him off here, and then we have this guy here, and this guy here. And then what I'm going to do is I'm going to go back and I'm going to kind of erase these lines, because if this is the front, then you can't really see these lines here. Whoops, those lines there. And you can't see these here. These are hidden. And so typically what you would do on a CAD program or that sort of thing, they would be shown as dashed lines to say that these lines are hidden from the perspective that you're looking at it currently. So what we need to do is we need to identify exactly what volume we have here. To do that, well, this is kind of a rectangular solid, and so we simply have some kind of a length here, we have some kind of a width here, and then we have some kind of a height. And so the volume is equal to the length times the width times the height. We just need to know those values. Well, if I go back up to my drawing, I get a little piece of paper here. Little piece of paper. I can cut out these corners, and I can just take a small piece of paper and approximate what I'm doing. So I'm going to try to chop out approximately the same size from each. You can get all kinds of fancy with this and do the drawing, take scissors and cut them out, but ultimately the math just needs the picture for guidance. It doesn't need it for absolute. So here we go. Here's our little piece. Now, when we do that, we're going to fold up that edge, but we're going to fold it right here along that line. So if I do that really quick here, so I folded it along that line, and now I have part of a box. If I continue this process through, I essentially did this, and if I open up the box to actually make the box, I can kind of see my net. So I don't know if this is really coming through all that well, but here's the thing that I had. It was spread apart like this, and now it's folded up. So the question is, what is this length here? What is this length here? And how tall is it? That's the real question. So if we do some analysis on it, the long length in this actually came from this measurement right here in orange. So that length then would be this 20 inches that we started with, and we chopped out a value of x here and a value of x here, which means we subtracted out 2x from that measurement. It's just a single measurement. There's no squares or anything. This is just a single length. And then if we go to, say, purple, and we look this way, then we started off with 17, and we also, wow, that is the weirdest 17 ever. Let's fix that. We started off with 17, and we still subtracted another 2x. So this length here is going to be 17 minus 2x. This length here is going to be 20 minus 2x. But now we need the height. Well, that's kind of odd. But if we take a look at just one of these sides, we notice that we cut out this little bit here and this little bit here, and we folded it up. But this length and this length were the same, and that was the x value. So when we fold it up like that, the height of this thing, the height of this fold is going to be x, whatever value we made x. So when we come down here to our box and we start identifying this, this width right here is going to be 17 minus 2x. This length right here is going to be 20 minus 2x, and this height is going to be x, just plain old x. That's all that it folded up. So now to find the volume of that, we just simply multiply its length times its width times its height. So we take that, and then we can say now v of x, because this is a function of x depending on the value that we choose. This is going to be 20 minus 2x times 17 minus 2x times x. You have three things multiplying, so that means you can do commutative property, you can do associative property, blah, 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 do whatever you want. I'm going to start with the distribution through the binomials, and yes, I am quite well aware of this thing called the dirty four-letter F word. I refuse to use it. So if you watched any of my videos on polynomials, you know I won't use this. It's bad. I'm not even going to say it. But what happens is you distribute. So I'm going to take this number here, and I'm going to distribute it as multiplication to those other two, giving me v of x is now going to be 340. 20 times negative 2 is going to be negative 40x. And then I take this number here to include its sign, and I do the exact same thing. So 17 times negative 2 is going to be negative 34x. Negative 2 times negative 2 is a positive 4. X times x is x squared. I take that whole mess and I multiply that by x. The nice thing is it's just going to raise the exponent on every single term of x by 1. So now my volume function here is going to be 340x minus, and this is going to total out, if I combine like terms, minus 74x squared plus 4x cubed. And I'm just going to kind of rewrite this in quote unquote the general form, which is decreasing exponents on x. So 4x cubed minus 74x squared plus 340x. And now whatever value of x you choose it to be, and that way you can manipulate the size of the box, you can then command your computer to go ahead and cut that for you. You can define x to be 1, 2, 3, pi, e. I mean, you can call it whatever you want. It doesn't really matter. The volume function will stay the same. And that's the beauty of mathematics. You can create one function, and now we created a function that quite literally builds every box you need as long as it fits this structure format and has this net. And that's it. If you change anything about this, this whole formula could change. It doesn't have to, but it could. All right, that's how you kind of conquer those. Again, if you guys have any questions, let me know. If I catch them on YouTube, I'll try to answer them. If it needs another video, I'll try to answer another video. All right, talk to you later.